Thank you very much. Thank you for coming back. Thank you for even bringing the cat. That's nice. Okay, so last time we talked about entropy, and this is what we are going to continue at the kind of most of the time. And then at the very end, I also want to introduce some kind of new concept called relative Poisson boundary. So first of all, so what was the setup? So we had G acting on some nice space, and just for the definition of entropy, we only needed to be non-singular. And we had a nice probability measure on the group. And the Fürstenberg entropy was defined as x and n, as I take minus log of the Radon-Nikodym derivative when I'm shifting with a group element the measure, and I'm integrating over all x, I'm integrating over all g. So I have here d nu x, d nu g. Okay, last time I just very briefly in the end mentioned, this is always positive and it's 0 if and only if the measure is actually invariant. But since I found out actually I do have some more time, so let's maybe just prove this. So I want to give a proof of one of the things which I said last time, namely that the entropy is always non-negative, because also someone asked me in the break and was wondering, well, is it okay for non-singular, or do we actually need stationarity for this? So let's just kind of convince ourselves with an easy exercise that this actually works. So what is it what we are doing? We use Jensen's inequality. Because minus log is a convex function, so I can use Jensen's inequality, which gives me that this will always be greater or equal of, I let this integral here and I put minus log here of the integral of x of d g inverse nu to d nu d x, d nu of x, and d mu of g. Okay, what can we do next? Now we kind of just, if we know what Radon-Nikodym derivative is, then now things become easy, because what is written here, well, this whole expression is just g inverse of this. So this thing here is just d of g inverse nu x. So what we have written here is the integral over g of minus log of nu of g inverse of, well, I'm integrating over all of x, so of x to d mu of g. And now? Exactly. So what is this? Can you tell me a number which is this? Yeah, it's really 1, because if I'm acting with a group element here, I still get the space. So this is just equal to 1, meaning that I have minus log of 1, which gives me 0. Okay. And then it's just, in Jensen's inequality, it's also concluded that this is, so it's equal if and only if the expression is constant, meaning that we have d g inverse nu d nu being constant, which means that, well, a priori it could be that I have still some kind of what should I, yeah, means that I mean, yes, let's skip some details. So it means that I have really, this nu is g invariant. Okay, good. Are there questions to entropy in general? No? Good. Then maybe a question which you should ask me, well, but what kind of values do we get when we look at entropy of something? I think even this question was last time to some extent. And so I promise you I'm saying something about it. So we can consider the entropy spectrum of G and mu. This is an interesting object people study. Well, it's just a collection of all entropy values of some space where I just require that G acts on this space ergodically, and we want it to be mu stationary. We will later see something where we don't have stationarity, but let's just for this. So this entropy spectrum, so this is a bunch of numbers. Can you tell me what kind of range of numbers is it included? I mean, where does it sit? What's the kind of worst case thing we can get? What's the most we can get? Where does it sit inside? In which interval? Exactly. So 0, definitely we start with 0. And we have seen that the maximal thing is the entropy of the Poisson boundary, which is the same as just a random walk entropy. So if we have, or let's see, if we have discrete group, yeah, let's say we have G discrete. I anyhow need it only for this. Let's say G is discrete, then we can really just have random walk entropy of G. Okay. And so now I said a lot about these properties. Now I want to go back to algebraic properties. And there is a nice result of Amos-Neveu, which I, in a different language, mentioned already before, from 2003. Again, this is a countable group, which says that if I have the G has T, property T, then there exists an entropy gap. What do I mean by this? This means that there exists some number, I don't know, let's say epsilon, such that the entropy spectrum of G and mu is contained in, well, 0 I can attain, but or maybe I can attain, depending when I have an invariant measure, then I can attain it. And then I'm only starting at epsilon. Okay. Now you should ask me, but what about the reverse direction? So the reverse direction does not work in this setup, but Louis Bowen, Yaya Hartmann, and Omar Tammuz proved some kind of reverse direction. In 2015, which says that we have property T if and only if there exists an entropy gap in the following collection, namely we take the collection of all entropy values where I have that, again, I want ergodicity, and I want that it's so-called properly non-singular. So properly non-singular means that, so it should be non-singular, and we don't want that this measure is actually equivalent to an invariant measure. what do I mean with equivalent? It means that it should not be absolutely continuous in this direction and absolutely continuous in that direction. This is the symbol of having the same. So it should not have the same mass. It's then an invariant probability measure. And yeah, and so yes, and also they in another paper, but the same authors gave an example of a group which has property T. Which has not property T but still has an entropy gap. In this sense, in the above sense. Okay. I will go to the other board. Okay, now so we have understood this side. How about examples where we can get all entropy values? So Lewis Bowen, also in 2013, he showed that the entropy spectrum of the free group on two generators with respect to the simple random walk on its or R generators, doesn't matter. I mean, whatever. Is really realized as the full interval. And the technique he used is very nice. It's with invariant random subgroups, so IRSs is what he used. So it's like kind of for the sorry you can compute it. It's not so difficult. It's I don't know log of it's I mean it's like I mean what do you have to compute? You have there it's just sum of and then you will have something 1/4 times log of, so it's computed. It's an yeah, and it's not difficult. It's a good exercise to compute it. It's I don't know minus log of the generators whatever. It's something. It's not a difficult thing. But the surprising thing is to understand the factors of the Poisson boundary here. That's the thing. Like we don't know. I mean, we cannot write them down very explicitly. That's why Lewis Bowen was doing all this with IRSs. So basically, he considered random cosets, and then he showed that okay, there is a nice entropy formula, and if I just take the product with an invariant measure, I don't destroy the entropy, so I can still see really the entropy values of this. And then he showed that this is all true. Yeah. Retrieve. I don't know what you mean with retrieve. So yes. This yes, of course. Yes, I mean it's something. Yes, it is really. I don't. It's you can't really compute it. It's not. I think I did it sometimes, but it's really yes. It's really something like logarithm of I don't know something, and then you have and all these things they depend on R. Yeah, it's something like this. They all depend on R. It's a number. It's a very simple number. Do it for 2. We can also do it. So no, I mean this with the range, it's like I fix an R and then I want to have all the entropy values. And no, it's not linear, it's log of something which depends on R. So it doesn't depend. I mean, if you want to, we can do calculations, but it's really not a big thing, but it's maybe I can, if you want to, I can do the calculations in the break and then tell you the exact. But it's really it's a simple number. It's something like no. I mean this is really for finite R. No, so for simple random walk, we will always have that this is actually finite. And then this result was also generalized by several authors which I mentioned, but also by Jeremy Brussels and Tierney Seng, and they assumed that the entropy has to be finite. So in order to say something about the values, usually you want to assume that the entropy is finite. I'm going to write it down in a moment. So, okay, so this was generalized then by Yaya Hartmann and Ariel Yadin in 2017, where he, instead of simple random walks, he considered some mu which is finitely supported. And this then was generalized by Jeremy and Tierney. I mean, they actually proved something even much stronger, which I will say in a moment also, where you want to have the entropy of the random walk should be finite, and you want to have a logarithmic moment. And then still in all this, under all these assumptions, we still get for the free group, we can attain every value which we want to. So the free group is really rich in terms of having factors. And what they actually, they showed something much more, namely they showed that also that the entropy spectrum of SL2R and mu with the same assumptions, or let's say compactly supported, and plus some assumption, whatever. I don't want to go too much into the technical details, is just zero, and really also here, the entropy of the Poisson boundary of SL2R and mu. And okay, now you have to ask me, okay, what about SL3R? What do we know about SL3R? There is a gap, exactly. So definitely we will have something like this, and they even showed, yes, it can be realized. It's not only included, but it's realized gap. And then I have some, let's say, let's say G mod P1, G mod P2. Okay, now let's entropy. How did I write it down? Yeah, okay, entropy of G mod. Some P1, some new one, entropy of G mod P2, new 2. So in general, the Poisson boundary of SL and R can be realized as the group modulo. So maybe I should write here SL3R. SL3R. Modulo its minimal parabolic subgroup and some probability measure. Okay, now what about for 4? Yeah. Yes. It's not this is not the this is not the Poisson boundary. Yeah. You always definitely you have to have wait, which one is the this one is the bigger, this one is the yeah. So you want to have that P1 should be bigger than P2. Yes. Yeah. Yes. This is also can be written as the if yes. Exactly, the Poisson boundary is the quotient. And so actually they showed more general that the entropy spectrum of SL and R and mu, and also of basically all the lattices there, can be realized as the union of some intervals. I basically it's again of this form. I don't want to write it down. For some index I, which goes in from 1 until n-1. So what does it mean? It means then for 4, we would have 4 minus 1 factorial, and so on. So we kind of, everything splits more and more, and we kind of get more fractal than fractal with higher degree here. Zero is, I also wrote it as an interval, but I mean, yes, yes, 0 is realized. So this is basically, here you have 2, the next you have then 6, and so on and so forth. Okay. Good. Okay, so we talked now a lot about this kind of entropy spectrum, and we have seen that all boundaries, they are ergodic, and by definition they are stationary. So what about restricting this whole set to the collection of boundaries and see what we can get there? So this is what we call boundary entropy spectrum of G and mu, which should be the collection of all x nu, where this is just the mu boundary. Okay. I mean, clearly this sits inside the entropy spectrum of G. Okay. So in particular, if I have a gap there, then I have a gap there. If I have a gap there, then I have a gap there. So, okay. So one advantage of doing this is that for certain groups, we can kind of really very explicitly show some interesting behavior, in a sense that for the same group, if we take different probability measures, we get very, very different entropy spectra. So this is joint work again with Michael Björklund and Yaya Hartmann, where we say, so the group which we consider, did I write it here or gamma? Okay. G should just really be, I want to take the restricted infinite product of lamplighter groups. So I take lamplighter group, but I take it infinitely often. One can also do something similar with Armschlag solid. And then there exists two generating probability measures mu1, mu2 in prob of G, such that on one hand, the boundary entropy spectrum of G with G mu2 is a Cantor set, and the boundary entropy spectrum of G and mu2 is an interval. Okay. In fact, it's a very kind of explicit construction, namely, so in fact, we have, so if you give me any sequence which is summable, which you want, so for every sequence, let's say beta n of positive numbers such that it's summable, real numbers in R, we can find a probability measure which is generating, such that the entropy spectrum, the boundary entropy spectrum of G with this probability measure is the subsum set. Subsum of this beta n. What do I mean by this? This is the collection of all sums. Let's say I in I of beta I, where I'm running over all possible indices here, there. So I just take the collection of all. You give me some sequence, and we can consider the collection of all different sums which we can build with this sequence. And in fact, really, the entropy will be this subsum set. And then it's so how to get from here to here. There is an old result of Kakeya in 1915, which says that if we have subsumption set, and if beta n decreases, if I take the rest of it, so if I take k from n plus 1 until infinity, and I'm summing this all up, and this is smaller than the previous one, then I do get that the subsum set of this beta n is Cantor. Is Cantor, and if I get it's smaller or equal, then I get it's an integral. So in fact, we just show this subsum thing. The rest then just follows easily. Okay. Are there any questions so far? So it's like, so the proof is not too difficult, and basically it uses some things which we have already seen in the first lectures, and some kind of calculating entropy, which maybe, I don't know, helps them to calculate then the entropy of some more simple things. So I would like to give it, also before, there is one, let's say, main lemma which we use in this proof, which is interesting in its own and maybe useful, or at least, yeah, some people have also used it, which I want to state. And it's also not difficult, so let's really do this. So if we have G acting, let's say X is compact and metrizable, and we have a continuous action. And if we have two probability measures, mu1 and mu2, on some group, which are of course generating. And so here I don't need to have discrete, so let's say spread out also. So this works in, yes, in general locally compact groups. And I want it such that they are commuting in a sense that mu1 convolution with mu2 is the same as mu2 convolution with mu1. Okay? Then I can conclude the following. Namely, first of all, so if I have a probability measure on X, then this probability measure is mu1 stationary if and only if it's mu2 stationary. Second, if nu is mu1 stationary, equivalently mu2 stationary, then we have that nu is mu1 proximal if and only if it's mu2 proximal. Okay. So what do we get from that? What does it mean for a boundary of mu1? If I want to consider, so let's say in particular, so if I consider boundary of G and mu1, so this should be the collection of all mu boundaries, mu1 boundaries. What is this? Under this commuting assumption. Exactly. This is the same as just the mu2 boundaries. Okay, so it's a very nice way of basically, so somehow the whole, this was really a key lemma to prove this, because it's like, if we, somehow we do understand maybe the Poisson boundary and boundaries for some measure, but actually to have the entropy in a certain way, we would need it for another measure. And we can do it as long as the measures are commuting. So we have some freedom in changing the measure as long as we don't destroy this commutativity property. What do you mean? I don't think so. I mean, just take trivial boundary. Also, no. Well, sure. Yeah, okay. I would have to think about it, but yeah, that's okay. Let's do the proof of this, because the proof is just ergodic theory, and maybe some people here in the audience like ergodic theory. So the proof relies on the following well-known fact, namely, if I have nu, how did I write it? Nu and eta are probability measures in my space X. And let's say just I have one measure here. So if there's mu stationary, both of them, with respect to the same measure, and I have that nu is absolutely continuous with respect to eta, then it immediately follows, did I say ergodic? No, sorry, ergodic. Ergodic and mu stationary, then it immediately follows that nu one has to be, nu is the same as eta. Okay. The proof of this is basically just the ergodic theorem. Okay, because what does the ergodic theorem tell you? It tells you that, okay, if you have a sum of some f of some g1, gn x, then this will converge. So 1 divided by n, let's say k equal, the rest of 0. Yeah, n minus 1. This will converge, well, on one hand, it will converge to nu of f for nu almost every x in x. And on the other hand, this will converge to eta of f for eta almost every x in x, just by the ergodic theorem. Well, and then the only task which remains is, well, find a common normals, find a set, find one point, actually, we just need one point, such that for the same point, this holds. Then by uniqueness of the limit, it has to be the same. Okay, so what you actually need to do is you need to take this absolute continuity condition to say, okay, on a conal set for nu this works, therefore it's a conal set for eta, and you can find a point. Okay. Okay, so let's use this fact and continue in the proof. So let's put here. So without loss of generality, I want to say that, did I write first like, okay, that nu is ergodic. Why is it? So the ergodic ones, the ergodic probability measures are extremal measures in the collection of stationary probability measures. So if I show that it will be stationary for, if I show the extremal will be, all the extremal points will be stationary for one if and only if they are stationary for the other, well, then also all combinations will be stationary for one if and only if they are stationary for the other. So it's enough to restrict to stationary to the extremal measures. Okay, so what do we want to do? Basically, we have here, should I maybe, no, yeah. So we have here three ingredients. So we have here, I don't know, one. Did I say first? Yeah, let's say 2 and 3. So we need to show that we want to say something that we have all these 3 criteria are fulfilled, therefore measures are the same. So first of all, we want to show, yeah, let's take a new board. So first we show that we will show that mu2, so did I say okay, sorry. So let nu be mu1 stationary. Sorry, I'm only proving the first one, so I'm only proving the stationary result. The other one is also not difficult, but if there is time, I can do it in the end. But so let nu be mu1 stationary. I want to show that it's also mu2 stationary. So first we show that we will show that mu2 convolved with nu is absolutely continuous with respect to nu. Okay, so what do I want to conclude? I want to say that nu2 convolved with nu is equal to nu. So I say this thing is now playing the role of my eta before. Okay, and I want to say this eta is the same as nu, then I have said that is mu2 stationary. Okay, so maybe so as this mu stationary, to show is that mu2 convolved nu is equal to nu. So first we show that it's absolutely continuous. So what do? We take mu2, so we say let nu of some measurable set be 0. What do we need to show to say that it's absolutely continuous? Exactly. We want to say that it's 0 also here. So let's just look at it. So we have here mu2 convolved nu of A. And is this the way I want to say it? Yeah, okay. Yeah, okay. I will need one more step, but yeah. So I have nu of G inverse A of D mu2 of G. Okay, so how can I say now something about this expression? What kind of property could I maybe use? Huh? So I know that this here is 0, and I want to say something implies that also this here will be 0. What is it? Why is it true? Not invariant, but it's quasi-invariant, exactly. So it's non-singular. non-singular. We have seen stationary measures. If I have a generating probability measure and it's stationary, then it will be non-singular. So therefore, if this is 0, then also this has to be 0 for all, for every G. So this means here I just have zeros. So I have just zeros and I'm done. Okay, so good. First thing is good. So next thing, show the second thing. Is it second? Yeah. Okay, I want to say that, yeah, that mu2 convolved with nu is mu1 stationary. Now this is the only point actually where I'm really using this commutativity property. Namely, indeed, I do have that. So what do I need to check for stationarity? I have mu1 convolved and then with this measure. So I have mu2 convolved nu. And now I know that they are commuting. So I have the mu2 convolved mu1 convolved nu. But my assumption on nu was that it was mu1 stationary. So nu is mu1 stationary, meaning just that I have here mu2 convolved with nu, and this exactly shows the stationarity. Because I take this measure, even if it looks weird, I take this measure, I convolve it with mu1, and I get out the same measure. So it's stationary. And the third thing is that we have to check ergodicity. So what do? We say let A be such that it's invariant. Did I say minus whatever? All G in G. Some nice measurable set. And we want to say that this measure charges this set A either 0 or 1. So we have mu2, yes, mu2 convolved nu at the set A. This is by definition just nu of G inverse A of d mu2 of G. But well, what is G inverse A? Well, by assumption, this is just only A all over. So I have here just, is it what I want to say? So I have just nu of A. But I do know without loss of generality, nu is ergodic. So that this only lies in 0 or 1. Here, since nu is ergodic. So also check with this. Okay. So I have checked all these three conditions. So 1 plus 2 plus 3 implies by this fact, which I wrote, that mu2 convolved nu is equal to nu. Okay, and this proves the first statement. The second one is also not too difficult, but let's not do proofs all the time. Okay, maybe let's do proofs all the time. I want to give you now the proof of this theorem which I wrote. Okay, it's a bit technical, but it's not too difficult still, so let's bear with me. So let's just take any mu0 in probabilities of the lamplighter. And I want again, of course, generating. I want to have that. So the thing is, I really want to have a random walk here, which only gives me the Poisson boundary and the trivial one, and it should not give me anything more, because I really want to get exactly this subsum set. For the interval, I could get, I don't care, if I have more factors, even better. But to really exactly obtain the subsum set, I want to somehow control the amount of factors which I have. So what can I do? I can say this should be lambda absorbing. With this definition, and lambda was this, what I said in the second lecture, this commensurated nice subgroup of C modulo 2C here, semi-direct product 0. So it should be on my coset space, it should be invariant with respect to this commensurated subgroup. And I want that it should have a drift. And I want to have that the entropy, the random walk entropy of the lamplighter and this mu0 should be finite. Okay. One can find such a probability measure. It's actually not too difficult to get this assumption, just take it finitely supported. And we have kind of seen by the before thing that we know how the lamplighter looks, the Poisson boundary of the lamplighter looks in this case, and that it's prime, so that there are no non-trivial factors. So somehow by the before, it implies that the only mu0 boundaries are the trivial one and the Poisson boundary. Okay, now let's take, it's still in the proof, but I write it here because I need more space. Let B is this summable, the nice sequence of positive real numbers. So any of it's given. What do I now want to do? I want to now construct something that the entropy value, so let's first be kind of slow. I want to have that, here. Let's just try to get something where I want to say, I want to have a probability measure on, let's for simplicity just say for the lamplighter, such that the entropy value is one given beta, one beta k. So I will be a little bit, I will later say it more detail, but okay. So just maybe observe that if I define some mu k, let me here write it mu k tilde, later it will be mu k, which would be beta k, later there will be something, but plus, okay, I only want to judge this. I don't want to judge the rest. So what do? I just take Dirac measure at the identity. This is a very kind of degenerate random walk if I'm just staying at the identity. I'm not doing anything. I don't change the entropy if I'm just standing at the identity. Okay, what do I have to write here in order to make it a probability measure? Just a wake-up exercise. So I have here this mass and I need to get rid of this mass. So let's say, okay, whatever it will be, and then beta k. Okay. So I put the good mass here on my mu and the bad mass on my standing at identity. Let's calculate what the entropy of this will be. It will not be, this is why I let some space here and we'll write it later. We have to be a bit more careful, but let us just, as a first attempt, kind of calculate now what is the entropy of this. So if I have the entropy, I didn't tell you what this mu measure is also, but let's say it is a nice measure on some nice space. Let's say I have mu tilde of k. Let me not write x because it won't be x in the end, but on some nice space, and we just want to calculate the entropy. So what do? We set in the formula, we have integral over G, we have integral over C, we have minus log of the Radon-Nikodym derivative of G inverse of theta to d theta of x, let's call it C, to d theta C. And what do we have now here? D of, now I have my random walk measure here. This would be my mu, but my mu is this mu k tilde. So I have here d of beta k times mu plus 1 minus beta k times Dirac identity. Okay. So what do I get here? Well, now we have just an integral which we can compute. Well, this beta we can put outside. So what do we have here? We have here beta k of the entropy now of mu of this nice space holding space plus what is left over here. How do I get this? I have here, of course, this, let's say 1 minus beta k. Then I have integral over C, and everything will be 0 if I take this G integral. Beside what? If I just want to evaluate this integral of G with respect to this probability measure. So what do I get? Exactly. So everywhere I'm 0, the only thing where I'm not 0 is that identity. So I have written here log of the identity inverse theta d theta of C with respect to d theta of C. But what is this? Exactly. This is just 1. I'm not doing anything. If I don't want to shift the measure, my Radon-Nikodym derivative will be just 1. So I have here 0. So the whole thing really here, the outcome of the whole calculation is beta k times the entropy of mu of this space, which is nice. But now we don't want to have this thing. We only want to have beta k. So we need to get rid of these things, which makes the proof a little bit more technical. But it's not that much technical. So basically the main ingredients is really like kind of, I take a product of spaces, all of these spaces are prime, and I know how to kind of construct really by hand the measure such that it gives me exactly this entropy value. So after the proof, we can make a break. So what is so this was kind of the heuristics, and now let's go to a little bit more. So what do we want to do in this proof? We take Wn, some increasing sequence, namely increasing sequence to infinity of positive numbers, real numbers, such that still if I take these weights on my on my sequence, I don't destroy the summability property. So the k of beta k, it should still be summable. Okay, I can do that. And now I want to have, let mu, now I tell you what this mu over there is, be a probability measure on my lamplighter, generated of course, such that this mu commutes with mu 0, and such that the random walk entropy of lamplighter with mu should be 1 divided by W1. So this will kill me this thing here. And these W's are exactly the things which you should put here in the placeholder. It's also this thing is not too difficult to find, and this exists. One can just basically similar to here, just take some measure. Yeah, maybe I don't. If people want to know more, then it's okay. Okay, so now I can basically, so the thing is like, why is it necessary to have this mu0 and this mu? The thing is that we can't be sure that we can find a nice lambda absorbing. So we need to take a measure which understands the Poisson boundary and which gives us primeness. Then we take a measure which kind of kills this number. And we take all the things in such a way that they are commuting, so we don't change the amount of boundaries. So yes, so set mu k now. This is the real mu k now. So I have beta k times wk times mu plus 1 minus beta k wk of Dirac at the identity. And then I can define already this probability measure mu beta from the theorem, which is just given as, so I take the sum m equal 1 until infinity of 1 divided by the entropy, random walk entropy of the lamplighter with this mu. I did I do a mistake? No, it's okay. Of mu0. I hope I did. Okay. Of 1 divided by w n minus 1 divided by w n plus 1 times mu1 times and so on times mu n. Okay, this mu beta is a probability measure on the product of all these lamplighters. Okay, and this indeed, should I say something? Yeah, okay, maybe to say something. So I mean, this will be positive just because I had a decreasing sequence. It's not too difficult actually to show that it's a probability measure. Okay, I'm not too sure about this. Okay, and let me call this number here just alpha, because things will be otherwise get a little bit messy. And why is this measure nice? Well, actually this measure mu beta commutes with the product, with the infinite product. So if I have here mu1 times mu2 times and so on, this is the same as if I take mu1 times mu2 times and so on with my mu beta. Because what do I have? I have here, well, I have some finite product. Then I have here some infinite product, and it doesn't matter which number I take it because the infinite product is determined by some cylinder sets. Okay, so this means in particular, we know that the boundaries are the same. And we know how the boundaries for these infinite products are, because we know that they're all prime. So we have here the boundaries of this lamplighter and mu beta is the same as the boundaries of the lamplighter and this infinite product. I equal 1 until infinity of mu I. And these boundaries we do understand very well, namely, this is just exactly the all the possible, basically, I mean, I have only, for each of them, I have only the Poisson boundary. And then I can choose, okay, do I want to judge it or do I don't want to judge it? So do I want to take this Poisson boundary or not? Meaning that I have really here the product over I of exactly the same thing, namely the Poisson boundary of lamplighter of mu0, and I'm running over all I in N. Okay, these are all what is the Poisson boundary? Maybe I didn't say. What is the Poisson boundary of this whole product of the lamplighter, if I take just the product measure there, and each of these product measure just gives me primeness, well, it's exactly the product over all n. So what are the factors? What are the kind of possible kind of downstairs things, factors of my huge big thing where I have everything? Well, just all the subproducts kind of. Okay. And okay, the rest is just calculation. And so now we have h mu of the product of some I. Let's calculate it of some boundary of lamplighter and this mu 0. This is just, well, we have the sum over all these alpha n's. And then, so basically I do the same as I did before. I had here just a single beta n, and now I have just the whole sum of these things. So I have here the sum of h of what is remaining is this product, h1 times and so on times mu n. Of the product of all those I, but now I have to be a bit careful. It's not all the I's, but it's only the I's up until 2 times n. So I take the intersection with 1 until n. Of, maybe I should have given it a name, lamplighter and mu 0. Okay. So, here, this, but again, with the same calculation from before, we had, this was the product of this mu 1 until mu n, and they were actually just chosen in such a way that I have this beta k, and then the rest is not judged. So I have here really just a sum over this beta k's. So let me, okay, maybe I should be more, okay, so this is just the sum, I equal, and so if you have questions, just let me know. H mu, of this beta I, W I, and then I'm left over with H. This was this, the mu, sorry, this is the mu over there, from the Poisson boundary of the lamplighter with mu 0. Okay, and now, so what do I get? I have now this sum over this alpha n, and then I have the sum over this beta I, where I have I from 1 until n in n, Wi, and here, yeah, let's just write random walk of lamplighter and mu 0. So I haven't done anything, I just rewrote what is written here. This was, now what I can do, okay, so I only take those betas up until time n, but I can rewrite this sum also and say, okay, this is the same as taking I in I. And then I have the sum from n equal I. So I start at the position I. So I can take beta 1, if it exists in this, it will be judged by all the n's. Beta 2, if it exists, it will be judged not by the first one, but only by the next ones. So starting from 2. Beta 3, it would be start from 3, and so on. And then it judges all the things which are inside here. So I have here alpha n, and here beta I of Wi H random walk of lamplighter and mu 0. And so now let's again look what was this alpha i's. I mean, the alpha i's, they were just, so this was, let me write it like this. This was just 1 divided by H of the random walk entropy times 1 divided by Wn minus 1 divided by W. and plus 1. This was how we defined these alphas here. So what we do see is that the random walk entropy here, this cancels out, which is already nice. So we are left over with a sum, which is basically a telescope sum. So the whole thing here with the sum, this will just be 1 divided by W1, Wi, sorry, because all the rest just cancels out. So, but this means that this would cancel out with this one. And so we are then just left over with the sum I in I of beta I. And this is exactly what we wanted. Okay, and now let's have a break, and afterwards let's have a completely different topic. Okay. Sure. Okay, so I promised you to now very briefly start something completely new. So if you haven't followed all the things before, just feel free to come back now. So I want to talk about a concept. We have already seen relatively measure preserving maps. So we had a factor map, and it was relatively measure preserving. If we look at its disintegration measures, then really the disintegration is preserved by this probability measure. Okay, so maybe I should say, so the whole title of this whole thing would be, this was I think the fourth thing, is relative Poisson boundary. So now we can define something where, I mean, this is a rather strong assumption, and we try to weaken it, and we weaken it the same way then invariance is weakened. So this is basically an invariant something, and so I want to have now a stationary something. So I say that the same factor map thing here is called relatively mu stationary. Again, mu is a probability measure on the group. Some nice generating measure. Stationary. If what holds, what would you like it to do? Exactly. So basically we want to integrate over all these g's. So we want to have that nu y is the same as, now I take the integral over all of g of, now I need to put everything on one side. So I have here g nu g inverse of y d mu g. And this should hold for eta almost every little y in y. Because these disintegration measures, they're only defined for almost every y. Okay, so then we call it relatively stationary. Now you can ask me, well, is this might be a very stupid generalization? How does it have to do with the usual stationary definition which I gave you? So observe that G is stationary in the usual sense if and only if it's stationary with respect to a trivial extension, in a sense that I just have downstairs a one-point space. if this is relatively mu stationary. So it is really a way of basically extending this, let's say, notion which happens to have for really concrete spaces to a notion which happens between spaces. So I want to have, instead of I look at one space, I look at the relation between two spaces. What else do I want to say? Yeah, maybe let's just give you an example. So maybe also observe that, so what would be another way, what would be something easy where we see the stationarity? So if we have that, if we have a diagonal action on a product of two spaces, and this map, this factor map down is just a projection, then this will be relatively mu stationary if and only if G acting here on X and nu is mu stationary in the usual sense. Okay, so in particular, I gave you the first class of easy examples. Is that whenever I have some G here, which is mu stationary, then we have that the projection here, and this projection is relatively mu stationary. Okay. Maybe, or do you want to see, or maybe, just the projection where I completely ignored, I mean, I just, also, yeah, I mean, the same, a projection from X nu times eta and y, yeah, y and eta, to y and eta. Maybe let's just, yes, it's just, yeah, it's just, sorry, yes, exactly. So just maybe just to convince you why this is true. I mean, what are the disintegration measures here? So I want to understand what is nu tensor eta at a little y. Exactly, it's just nu. And I mean, if you want to, you can write it also then Dirac at eta. So we do, as you said, so basically it's just nu, which means this whole thing is relatively mu stationary if and only if the nu is mu stationary. Okay. Good. So maybe another. I have until 10 past. Okay. 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 I mean, yeah. Let's see. So, if this is if we have downstairs eta, which is G invariant, then we have this is relatively mu stationary. Also, if and only if nu is mu stationary. Okay, this is, I mean, it's also not difficult, but it requires a line of calculations. Another nice thing is that if I take some kind of other factor, so let's say I have here some commuting diagram, let's say some C and theta here, and we have, let's say I have pi and sigma, and this really commutes with respect to J action and everything, then we have that if we have that pi is relatively mu stationary, then it follows that sigma is relatively mu stationary. So in particular, this will help us then to construct a maximal one in a certain class, namely then the relative Poisson boundary. But for this, we need another definition, namely proximality. So we say pi with the same notation as before is relatively mu proximal. Again, if the same holds, so we take the weak star limit of push forward G1 and so on until Gn. And now we want to push not nu, but we want to push this disintegration method. So we have here G n inverse and so on, G1 inverse of y. And this now should converge to also a Dirac measure. But what would this Dirac measure depend on? We will have a boundary point, which on one hand, of course, it will depend on the sequence which I chose. But it will also, of course, depend on this little y. Okay, so I have a boundary point of Gn of the sequence and little y. And this should happen for mu to the n almost every sequence and eta almost every y. Okay, so this thing here, again, this is a point here in my space X. Or actually, it will be in the fiber exactly, in the pi inverse of this little y. Good, so now I have already everything to define a boundary. Let's say we're in a compact setting. So definition, if I have G acting on X and nu, and we say this is compact, and metrized and so on, and Y and eta downstairs here, then we say this is a relative mu boundary if we have that it is a relative mu stationary and relative mu proximal. Okay. And then as a result, we just joint work with Tatumasi and my former master student Martin Klötzer. We have that, well, there exists a unique, I will say in a moment what I mean unique, maximal mu boundary, a relative mu boundary. So what do I mean with maximal? Maximal in which sense? Well, it's exactly this commuting diagram. So I have here, I want to have some space here such that, which goes down to some y and eta, so that whenever I have some other extension here, some w and theta, and this is also a mu boundary, then actually I should also have a map down here. And in fact, we can write down quite explicitly what this maximal one is. Well, what is maximal? Usually it's, if I have some stuff, it's always the product is the maximal thing what we can get. So actually what we have here is the usual Poisson boundary of G and mu times y and eta. And these are all the other mu boundaries. Okay. Okay, so maybe let me just say one, yeah. So one short, so okay, there is a nice result of Fürstenberg and Glasner, where they were interested in the question, okay, if you have a space which is stationary, but it's not a boundary, is it very far away from being a boundary? Can we have some kind of structural result of saying, okay, I can actually pass to a boundary, or what can I do? So this is Fürstenberg. How should I write it? Okay. So Fürstenberg and Glasner. Structural theorem. It's actually not that ancient. So we what do we have? I have to. Okay, I will add then some more stuff in this picture, but let me start with. So we have G acting here. Maybe I need more space. G acting here on some X and no. And this is okay, let me write it here. This is yeah, no. Okay. Let me see how I get in space. Okay, this is mu stationary, but not necessarily proximal. And they ask, okay, what is there not maybe a nice boundary somewhere around? And they say yes, indeed. So there exists a nice space upstairs here, which is not a boundary, but it is kind of close to be a boundary in the following sense. Let me write it maybe, I don't know, B and, wait, now I'm running out of letters. What did I use here? Sit. Okay. So this is a mu boundary. And this maps are nice in the following way, namely this map here is relatively measure preserving. So in particular, what we have seen is kind of the entropies of things will be the same if things are just relatively measure preserving extensions. So it's like kind of, I'm not losing too much information if I'm going from here to here. But still, this won't be a boundary, but this will be the boundary. And this map is, so they have a different terminology, but let me call this map maybe phi. And maybe let me write it here. And so phi, this map, it's not one-to-one, but if I take the limit measures, then it will be. So I have that, if I have W, and then let me write it kappa omega to, I will explain in a moment. And this is one-to-one, where kappa omega is the weak star limit of some G1 and so on until Gn of kappa and so on. Where and this W is exactly this sequence, so G1, G2, and so on. Okay. So this is a nice, so it's kind of, there is a nice construction doing this. In fact, this space will then be realized as this space times the probability measures on this space with some nice joining measure there. And so now naturally you can ask, okay, what can we do a relative version of this? And the short answer in 2 minutes is yes. Namely, what do we do? Okay, I mean, now I don't want to have this being stationary. I want this to be relatively stationary, meaning that I do have downstairs some y and eta, and only this map is stationary. The thing itself is not stationary. Okay, and what can we do? Well, yes, we can say, right, it's not a boundary. It will be a relative boundary. And well, this will not be one-to-one like this, but it will be one-to-one if I take here also G and inverse and so on, G1 inverse Y. And so this also depends on Y. So this all depends on Y, and then this will be one-to-one in this sense. And so this is then kind of the relative version here of this, which is also joint work with the same authors from before, so Tomassi and Martin Klötzer. Okay, so yeah, maybe just okay. So and yeah, really, maybe this W kappa can be really written as x times the probability measures on x, and I have a nice joining here of this and with theta. Okay. Good. So maybe let me end with a lot of kind of um, yeah, just saying that there is still a lot to do. This is basically the beginning of the project. This is not a completed project. But it's maybe also a nice kind of, I wanted to take it for the mini course because it's maybe a nice exercise just for students who haven't seen Poisson boundary before. Just do it again, but in a relative version. It's kind of a nice concept. Okay, so thank you very much for your attention.